Okay, units of measurement. Units are really, really important. And one of the problems I have with chemistry students is they don't want to write down the units. Let's look at this sentence. When my son was 7, he walked 3, and when he was 4, he could throw his baseball 8 and tell us that his school was 5 away. Does that make much sense? No. What the heck? If we stick some units in there, it makes more sense. When my son was 7 months old, he walked 3 steps. When he was 4 years, he could throw his baseball 8 feet and tell us that his school was 5 blocks away. Now that makes sense. Think about going to a fast food restaurant. What would you like, sir? I'd like 5. 5 what? A number 5 meal? 5 Big Macs? Just the number doesn't tell us very much. And it's the same in science. The number's fine. The number's necessary, but we need a unit as well. And so we have to talk about different kinds of units. The 2 most common unit systems are the English system and the metric system. So the English system is, inches, feet, pounds. That's what Americans commonly use, even though the English don't use it anymore. And then there's the metric system, which is vastly superior. Units matter. This is a great example. Back in 1999, NASA lost a $94 million orbiter because 2 groups of engineers failed to communicate to each other the units that they used in calculations. As a result, the orbiter descended too far into the Martian atmosphere and burned up. One group of scientists was using metric units, and one was using English units. It's an inch versus centimeter problem. $94 million. Matter matters, but units matter too. I'm mixing up my words now. Okay, so we tend to call it the metric system. It's technically called the International System of Units, or SI units. It's based on the metric system, and as far as I'm concerned, and as far as this class is concerned, they're the same. There are very subtle differences. We don't need to be worried about it. Here's a little table from your book giving some of the units. Meters are used for length, kilograms for mass, second for time. So second, the time units don't change. And then for temperature, instead of degrees Fahrenheit, we use kelvins. And we're going to look at that in chapter 3, so we're not going to worry about that just yet. So the meter is the basic unit of length. In the English system, we use feet and inches and yards. I want you to know that meter measures length, and I'd like you to have just a vague grasp of how large it is. It's about the size of a meter. I'm sorry, a meter's about the size of a meter. Oh my goodness, I'm losing it. It's about the size of a yard, just a smidge longer. It's like 39 inches. A yard is 36 inches. Okay, the rest of this, I'm behind in lecture, so I'm not going to talk about that, but that's just exactly how they measure it, just for interest. For mass, they use the kilogram. A kilogram is a little bit more than 2 pounds. So that just gives you a ballpark idea. So mass is not exactly the same thing as weight. Mass measures quantity of matter. Weight measures the gravitational pull on that matter. Okay? So weight is going to depend on gravity, but mass doesn't. So if you have a mass of, if you have a weight of, say, 100 pounds, and you go to the moon, your weight is going to change. It'll be about 1/6 of your weight on Earth. But your mass doesn't change. Because when you go to the moon, do you suddenly become incredibly skinny? No, It's just that the moon doesn't pull you down as hard as the Earth does. There are even slight gravitational differences if you stay on the planet. We're not going to worry about those. But I do want you to understand the difference between weight and mass. Mass measures amount of matter, and that's what scientists use. Weight is actually a force. It's the gravitational pull. Another common unit of mass is the gram. This is the one we use most in science, in chemistry, because it's a more useful size. So a nickel, which is 5 cents, has a mass of about 5 grams. So that can give you just kind of a ballpark idea. 5 grams is not a lot of stuff, but it's enough that you can see it. You can very comfortably hold it in the palm of your hand, right? And here's the relationship between grams and kilograms, and we'll talk more about that when we talk about the prefixes. But 1,000 grams is equal to 1 kilogram. Base unit of time is the second, and that's the same second we use in everyday life. We define it in a very crazy, exacting way, but we don't need to worry about that. Okay, so in the SI system, or in the metric system, we use prefix multipliers to change the size of the units. So I live in Reedley, I work here in Fresno. Would I measure the distance that I drive to work in inches? No, I'd measure it in miles. It's about 26.5 miles. Why wouldn't I measure it in inches? It'd be a really big number. I could measure it in inches, but it just seems like it would be ridiculous. We tend to adjust the size of the unit to be comparable to the size of the thing that we're measuring. If you are measuring the length of this room, what unit might you use? Yards or possibly feet, right? Because then you end up with a reasonable number. You wouldn't use miles or light years, right? So in the English system, we have these different units for different sizes. In the metric unit, in the metric system, we use the same unit, we just change the size of it by putting a prefix on it. So we pick a prefix multiplier that makes the unit a convenient size. So the prefix kilo means 10 to the third. Does that sound familiar? That was on the memorization quiz you just took. Some of you are like, darn, I picked the wrong one. Kilo means 10 to the third, 1,000. So 1 kilometer is 1 times 10 to the third meters. K is an abbreviation for 10 to the third. So a kilometer is 1,000 meters. Kilo is just an abbreviation for 10 to the third. So here's the table from your textbook. I didn't ask you to memorize all of these because some of them we use very rarely in this class. I think I went mega down to nano, except I didn't make you do deci. So these are the prefixes. And the multiplier there in decimals, that's nice, but I really think the factor of 10 is easier. I think it's easier to remember 10 to the minus 9 than trying to remember 0.000, I've already lost count. Right? So 10 to the minus 9 means nano. So conceptual checkpoint. Which is the most convenient unit to express the dimensions of a poliovirus, which is about 2.8 times 10 to the minus 8 meters in diameter. So it's a really small, you can't see it with your naked eye. So we've got 4 choices here. We've got megameters, millimeters, micrometers, nanometers. Nanometers. Actually, micrometers wouldn't be a bad choice either. Nano means 10 to the minus 9, right? So a nanometer is 10 to the minus 9 meters. So this would end up being 28 nanometers. So that would be a convenient unit. Micrometer would be okay. This is 10 to the minus 6. So then it's going to be less than 1 micrometer. Derived units are those that are formed from other units. There are many units of volume that are derived. So hopefully you remember, if you have a cube or a square prism, you've got a length and a width and a height, right? And the volume equals the length times the width times the height. If those are all measured in centimeters, then you get centimeters cubed as your unit. That's a unit of volume. It's derived from centimeter, which is a unit of length. Any unit of length cubed becomes a unit of volume. So cubic centimeters, cubic meters, cubic millimeters, all volume units. Those are we tend to use those for solids. We do have some volume units that are not derived, liters and milliliters. Milli is the prefix that means 10 to the minus third. So 1 milliliter is equal to 10 to the minus third liters. A liter is about the size of a quart, but what you're probably more familiar with is what 2 liters looks like, right? 2 liter bottle of soda. So 1 liter is half of that.